Hey guys, welcome to Gym Term 1B walkthrough. We're going to be going through the second practice midterm. Unlike the first one, no review. We did that in the first one. That's why it was insanely long. So we're going to try to keep short and sweet. And actually, I think I might just do both 2 and 3 in the same video. Although maybe not because the midterm did get pushed back. So kind of good news, right? Midterm got pushed back to next week on Thursday on the 11th. So increasing the amount of time that you guys have to study, which is always a good thing. Although it doesn't come for a good reason, right? It's because of the active threat right now in Davis. So, I'm just going to echo what you guys have probably been hearing. Stay safe, make sure, try not to travel at night. If you do, make sure to at least be in a group of 3. Stay safe, be alert. I think all of you could benefit from going on YouTube and looking up how to do basic self-defense. I mean, most of you should have keys, right? So all of you can, learn, basic self-defense with your keys, just to be extra safe. I know this is not the best time, and a lot of you are having a hard time studying. So, I'll tell you guys what, like your mental health comes first. Obviously, Dr. Nasiri also agrees because she's giving you guys an extra week. So it's okay if, for this week, you have to, take care of yourself over studying. That's totally fine, right? We have 7 more days to kind of figure out everything. So I would say, hopefully this situation kind of figures itself out, or something happens and then justice is brought to our victims. It's always the thing that we want, and we can wait for that, right? And I'm hoping that this resolves soon so that you guys have time to calm down and finally be able to focus on your academics. But put yourself first. If you're having a hard time, if you're feeling stressed, it's okay to take a couple days off. It's a very unique situation, incredibly unique situation, right? I don't think this was on anyone's bingo sheet that this was going to happen. So cool. Anyways, with that being said, I still do want to just get these out just so they're out so that you guys aren't just waiting, for next week for me to just get them all out. So I'm going to go ahead and do this. Again, we'll be going through multiple choice, predict the products. We'll do as many variants as we can, talk about mechanisms, and whatever we have it. Okay. Cool. All right. So first question, which alkene produces the lowest amount of heat after hydrogenation? And so heat of hydrogenation, right, kind of is an indirect measure for stability, right? If a system has a lot of heat, a lot of energy in it, right, it's not very stable. Low energy systems are what we consider with stability. So if we want if we looking for the lowest heat of hydrogenation, we're looking for essentially the most stable system. Okay. Now we'll ignore the alkyne for now. So we'll ignore this for now. It's obviously not going to be the answer. We'll look at the alkenes for now. Generally speaking, when it comes to alkene stability, what stabilizes alkenes are donating effects. So the most prominent and the most understood by you guys is the hyperconjugative effect, right? Where we take an alkene and we just give it an R group, right? That hyperconjugative effect where we are donating electrons hyperconjugatively into the alkene, right? That is our donation effect. That's our stabilizing effect. And the more of these R groups that we have, the more stable our system is. Now, in terms of the disubs, there's quite a few of them. Okay, but for the most part, you guys should understand that cis is less stable than trans because they both have the same hyperconjugative effect. So we look at steric effects, right? And so sterically, cis is more hindering than trans. There's also the geminal, which I believe in this class you'll just have to consider is about the same as cis, which is not always true. But again, we're just looking at, look for trends. More stable than this would be the trisub, right? And then more stable than the tetrasub, okay? But again, it's donating effects that are stabilizing our alkene, right? And in terms of R groups, hydro, I meant to write hyper conjugation, right? That's the term we're looking for. So that could potentially be a vocab term in a question in a multiple choice, right? What's the effect responsible for the stability of alkenes with increasing substitution? And it's hyperconjugation. Okay, cool. So looking at these guys, we can see hyperconjugation is definitely going to be the major key or major thing at play. We have a monosub, we have a disub, and a disub. So clearly the monosub loses in terms of stability, right? Because we want the lowest heat of hydrogenation, so we want the most stable figure here. But when we look at the last two alkenes, we have this disub and this disub. I mean, they're both trans, so we can't really, say cis trans isomerization is what, breaks the tie here. they're both disub. I mean, what else could be the thing here, right? What else could we look for? In an instance like this, where I'm a student, I don't know what to do. I try to look for a pattern. I try to look for, this alkene's over here and this one's over here. How might that change the problem, right? What else can I look for? And I noticed that in this ring, there's also a bunch of double bonds, right? There's also a bunch of these double bonds. And I mean, all that feature was present in all of them, which is why we didn't really have to focus on it. But now we should, right? We have these pi bonds in this ring, and in the left figure, right? When the pi bond is on the left side, we notice that the p orbitals or the pi bonds are all adjacent to each other, right? In the right one, right, the pi bonds are not adjacent to each other, right? We have this sp3 carbon in the middle, right? So what happens when p orbitals are next to each other or pi bonds are adjacent to each other, right? What's the effect, or what effect can happen, or what effect might we have on the stability of the system if this is the case? We're looking for a word here. That word starts with an R, ends with an assonance, right? This is resonance, right? Or conjugation. And conjugation will always lower the energy of the system. Okay. Or I won't say always, because if I say always, then someone will find a counterexample. For the most part, resonance does lower the energy of the system because all these p orbitals can mix, and now the electrons can travel through this p circuit, right? This p orbital circuit. It's like little cars in a NASCAR race, right? On the other hand, this pi bond's isolated, so it won't be able to resonate. Therefore, its energy content is going to be higher. Okay, so looking out for this type of effect is what takes a B student to an A student, right? Not only knowing what you learned in class, but also applying older material, right? In the sense that resonance stabilizes a system, right? Or it has the potential to stabilize a system. Okay. This also means that if alkenes are more stable when they're capable of resonating, right? This also means that you guys can make some very typical tough break. You guys can break some very difficult tiebreakers. For example, this question that shows up on one of your practice exams, where we have an alcohol that we are dehydrating, right, into an alkene. Now, normally we just look at HA and HB here, the beta carbons, and we just say, okay, which hydrogen is more substituted, because then there are these E1 conditions, we just go with the more sub. But again, when I kind of draw both the alkenes here, right, this one or this one, they're both disub. So you might be, convinced, oh, both form. But again, if we consider the energy content of the system, remember, this is thermodynamic. So we have enough energy to isomerize to the most stable form, right? This pi bond here is conjugated and able to resonate with the pi bonds in the ring, while this one here can't do it, right? It's isolated. And you guys will talk a lot about that in the upcoming chapter, about what especially what resonance does, right? How it makes things more stable. So for sure, the pi bond will form on this side here, and whatever reaction you do with it is going to do the reaction there. So if I epoxidate, right, it's going to epoxidate that way. If I dihydroxylate, it's going to dihydroxylate that way, stuff like that. Okay, so things to think about, right? This is how we take that C, B level of knowledge and we knock it up to an A level, right? That's how we do that. Cool. All right. So looking at that, that is our, sorry, I just had to kill a fruit fly. That is our answer. Now, if I go back to the alkyne, right, why did I instantly get rid of the alkyne? Remember, heat of hydrogenation hydrogenates pi bonds, and then reports, you're reporting the energy that comes off. So if it's every pi bond that you hydrogenate, that's heat's coming off. Well, alkynes are kind of unfair to use here because alkynes have an extra pi bond. So if we have 2 pi bonds on this alkyne versus the 1 on these guys, and again, we'll kind of ignore these guys for now because it's the same on all of them, so it doesn't really make a difference. But this extra pi bond is always going to increase the heat, right? It won't really have to do with stability of the system. It'll just have to do with the fact that an alkyne has 2 pi bonds, right? Alkenes have 1. So alkynes will always have more. In this case, this will actually be the most, the highest heat of hydrogenation. And that doesn't really tell us anything about stability. It just tells us that an alkyne has an extra pi bond. So it's not really fair, usually not very fair to what's the word I'm looking for? To compare alkynes and alkenes, because the alkynes will usually just have more simply because they have an extra pi bond. And also because alkynes are more, they do have a bigger geometric constraint. So on one of the practice midterms, I do have this question where I do kind of mix these guys together. Maybe now you guys can think about that, the fact that alkynes give extra energy, heat, and they have higher geometric constraints. You can think about which shape, is going to be the highest heat of hydrogenation or the least stable out of the two of these. Okay, cool. All right. So we'll call it on there for that. That's all, that's the hydrogenation stuff. Again, stability is the hyperconjugative effect. So you can imagine, right, if I have anything stronger than hyperconjugation, like an EDG or, like an oxygen donating atom, it's going to increase the stability of that alkene. Something to think about. Okay. Now, stability is all relative because, in fact, actually, albeit this might be a stable alkene, right? That's actually a very reactive pi bond, very reactive towards electrophiles, right? We talked about that in the first midterm, right? If I have like two pi bonds, one that's like juiced up with electrons, the other one's not really. Most electrophiles will go here, right? It goes to the more juiced up one. Well, if I throw an oxygen on this guy, guess what? This is incredibly juiced up. Almost in no case is the other pi bond really winning out. That oxygen is definitely going to take that electrophile before this guy can. Okay. Advanced topic, possibly not on the midterm, right? Just to kind of tickle your brains a little bit with what advanced OChem would look like, or not advanced, but like just the next level, the one beyond A, but just a little scratch in the brain. Cool. All right, so we'll move on to the next one. Which compound forms a chiral product after treatment with Cl2? So in this case, you just have to draw, right, the products of this reaction. So the anti-addition, Cl2 is an anti-addition. So we'll get this for the first one. We'll get this for the second one. We'll get this for the third one. And then for this one, we'll get this here. Okay. So, I mean, two of these, it's really obvious are not chiral. We have two chlorines on this carbon. We have two H's on this carbon. This is not a chiral carbon or a chiral system at all, right? This one here has two methyls on both carbons, not chiral at all. So it really boils down to these guys here. And so you could go back to thinking about what does meso mean, right? What does chirality have to do with or multiple chiral centers? How can we determine if something's chiral or achiral? Blah blah blah. We're here for the tips and the tricks, right? We're not here for the history lesson. So here's the tip and the trick that you guys want. When it comes to meso compounds, if you have a transalkene and you do an anti-addition, so think about what are things that do anti-additions, like X2, for example, right? And you have a symmetrical trans system, right? You will always form a meso compound. Okay, you'll form a meso compound, and the way you can prove it is if we look at this, right? The H's are trans, the X's are trans, and the CH3s are trans. So since the identical groups on both carbons are all following the same transness, I guess, or like they're they're all trans, this is a meso compound. Okay, we can then apply this to cis compounds and say if I do a syn addition, right, where I add two of the same thing. So come on, think hydroxylation here, right? This will also form a meso compound. Okay, and again, proving it by noticing that the H's are syn, the OH's are syn, and then the CH3s are syn. So since everything follows, they all have the same synness, the identical groups, right? This is a meso compound. Okay, so this is the trick. This is the trick, and this is how this usually shows up. Cis symmetrical. So you have to start with a trans or a cis alkene. It has to be symmetrical, and you have to be doing a symmetric operation on it. So an anti-addition of something that's symmetric, so XX, or you can do hydroxylation as well, right? You can do the MCPBA to hydrolysis to get two OHs here. That would have worked too. In terms of syn, there's not very many syn things, right? Like there's no syn X2 addition. There's only really syn OH additions. So OSO4 is kind of limited to this one. Okay. So with this one, since we know this is anti, right? To form a chiral product, right? This is a transalkene. Symmetrical trans and anti are going to make a meso compound. So we're going to go with the cis isomer. Okay. So this is the X2 answer. Let's say I did a dihydroxylation and I wanted to find the chiral product. So dihydroxylation, so OSO4 reaction, this would be the answer for OSO4. Okay. Cool. All right. Call it on that for that one. For C, lowest energy conformer in the reaction of 3-bromo pentane with NaOCH3. So recall, Na is just a metal plus. That makes OCH3 minus, a strong base, O minus. Remember, associate O minus with E2 reaction. So I'm thinking this is an E2 reaction, right? Think about what is the lowest energy conformer or the lowest energy transition state for this reaction. It is anti. So we're looking for the Newman projection that's not only correct, but also displays the most anti, the most stable conformer so that the E2 reaction can occur. Okay, so we can have this species here. I mean, this is 3-bromopentane. And so I guess it kind of depends on which way you're looking at. I'll just look at it this way. But how can I draw the Newman projection so I know which ones to cancel out and which ones to compare, which ones are correct? Super simple. This is a dot where you're looking at, and behind it is always a circle. Okay, so I'll have the dot, and I'll have the circle. Okay. Now I'm looking at the dot and I see this pointing up. So I'm going to go ahead and draw, or sorry, I'm going to go ahead and draw this pointing up like that. And then this will be in the back, just like that. Okay. Now just report everything that's on this carbon on the green on the dot. So there's an H, H, and a CH3. So CH3, H, and H. And then on the circle, there is an H, a bromide, and an ethyl. So an H, a bromide, and an ethyl. Okay. Now, because this compound is not chiral at any carbon, right? And you can confirm that it's not chiral anywhere. I don't really care where I place things, right? I'm not being super strict or super concerned about that. Because achiral means that you can put it anywhere, it'll just be right. Just make sure it's on the correct carbon, right? Don't just put Br on the front carbon because you're like, oh, it's achiral, put it anywhere, right? Make sure that it's where it's supposed to be. But now we have a correct system or a correct Newman projection that we can kind of compare to the rest of these, right? So the front carbon, or either the front or the back, because I guess we don't really know which way I was looking, but we know that one carbon should have an H, H, and a CH3. So when I kind of look here, I see CH3, CH3, H, and I see CH3, CH3, Br, right? Don't have what we need, right? I see here H, CH3, CH3, and again, I don't really see CH3 with 2 H's, so I know this is wrong, right? I check this one, I see the HHCH3, right? So I check on the back, there's an ethyl, H, and a Br, ethyl, H, and Br, so I know this works. So I can maybe I circle that accidentally because I'm like, oh, yeah, that's the right answer. I don't know yet. And then HHCH3 and then BRHCH3, CH2 in the back, so ethyl. So it's between these two guys now, okay? Now remember, when it comes down to the lowest energy, we want not only the anti-form, right? So we want the H and the Br, right? Because it's an E2, so we want an anti-H and Br. But we also, right, we'll also want the least amount of gauche interactions possible. So gauche interactions were those where carbon chains interacted with things larger than a hydrogen next to it, and it would cause some kind of uncomfortableness. So for example, CH3 and Br can have a gauche interaction. Br and H wouldn't really be gauche, and CH3, CH2, and H wouldn't be gauche, so these guys are kind of escaping it. But I mean, as you can see now, this one looks very nice. There's only one gauche interaction. Look over here, we have 2 gauche interactions where Br interacts with CH3, and the CH3 also interacts with the ethyl. So very, very bad that we have those interactions. I guess one thing I kind of said without saying it out loud is, the H and the Br are always anti in these, right? But prioritize your Gauss interactions first for lowest energy conformer, and then just make sure the H and the Br are anti each other in this reaction, or in these conformers. Looks like this guy's going to be the best one. Okay, cool. So very, very common question this is actually, because remember, E2 proceeds through anti, and it's always the lowest energy conformer of anti that we can get. So if I were asked to draw a mechanism for this through the Newman projection, which is a common question, right? I would make sure that the Newman projection look like this, and then I would draw my arrows as such, where I take H, ambiguously put in the middle, and then get rid of the Br, and then I kind of report everything else exactly where it is, right? So, oops, sorry. So CH3 and H, and then H, and then CH2, CH3, right? The cool thing about this is that this kind of tells you what your alkene looks like too, right? CH3 and H are on this on one side together, H and CH3 on the other side. These two are syn, the CH3 and the H, because they're on the same side, and these two are syn, right? The ethyl and the H. Okay, so very, very easy, cool way to very quickly, draw the product that you should form. Okay, and you'll also see that this also forms the trans product, right? Which we did say is the more stable product whenever we eliminate on a CH2. Okay, cool. So with that being said, it might be useful to just go quickly down here just because we have space and just kind of talk about how to answer this question for a chiral substrate, right? Imagine you were given maybe something like this. Yeah, let's say you're given something like this, and you have to answer for, what is the product of this reaction, and then draw the mechanism through a through a Newman, right? How can we draw how this would look? Okay, so again, the Newman dot in the circle, right? We kind of want to look down a bond. Since we're thinking about elimination here, right? And we want to eliminate on the more sub because we're using a small base, right? I'm going to go ahead and look down this way, right? I want to look down that bond because that's the bond that has the Br and the H. Since it's already anti, HA and the Br, I have nothing to worry about in terms of rotation or anything. It's kind of already set up for me, okay? So I'm going to be looking down this bond, and once again, we're going to do the dot in the circle. Okay, so I'll do the dot and the circle. Okay. Where things get kind of tricky is that we have two chiral centers, so things have to be pretty specific here, right? Things have to be correct. We can't just guess where things go. So here's how I like to do it, and how I always, tend to get these correct is I imagine that this face is actually mine, right? So me, right? I would look like this, with a very weird looking ear. Just kidding. But that would be me. And if I kind of imagine my arms in this scenario, right? The arm that's sort of pointing away from me would be my left arm. And the one that's pointing towards us right now would be like my right arm. So that kind of tells you, it kind of sets a rubric for you, or not a rubric, but it kind of sets like a rule for you as to where your wedges and dashes should be on your Newman if you're looking down this way, right? My dashes should be on the left side and my wedges should be on the right side. And then whatever's into plane with my body is going to be going up or down, so vertically. So for example, this ethyl, right, is in the plane, it's in the same plane as my body, that's going to go down, right? And so that kind of tells you that there's a Y shape in the front. But I also now know that the Br being a wedge is going to be on the right side, and the H being a dash is going to be on the left side. Okay. You can also then just set up everything else. You could look at the dash and wedges. You could also just look at the fact that Br and CH3 are on the same side, so it's got to be like that. And then HA and H are on the same side as well, so it's got to be like that. And then there is a pH, which is just phenyl. It's a benzene ring, by the way. This is what it means. That's just going to be on the plane again with my body, so it's going up. Okay, and this is my correct Newman projection. Now, again, I mean, it's already anti, so all I have to do is now draw the reaction. It's already in its lowest energy conformer. But now I can go ahead and draw this, and I will omit the colors this time because I don't need them, right? But, we got rid of the Br, we got rid of the H. So I'm going to have pH, I'm going to have CH3, and then I'm going to have ethyl and H here. And look at that. I now have exactly choreographed to me what my alkene would look like, right? Because I know H and ethyl are on one side, right? And then pH and H are on the same side, and CH3 and the ethyl are on one side together, okay? So I get specifically this here. If I look at the E and Z, this is E, okay? So I can go ahead and draw this alkene as my product. I guess you could have also already started with that because you can, again, it's already anti, so you could have kind of just drawn the outline and drawn this and seen, oh yeah, that matches up exactly the same. Oops, sorry, forgot the H. Okay, cool. So that's how you can do E2 eliminations via the Newman, and a very quick way to do it too. Okay? I imagine a lot of you are also worried about transforming Newmans into potential names or potential molecules to name, and there is kind of a general procedure for that as well, right? So let's say that we have something like this. The way that I like to do it is, again, the dot and the circle kind of guarantee you 2 carbons, right? Then you just kind of have to put things where they are. So if this is like the dot, this is the circle, right? The dot has an H, a Br, and this like 1, 2, 3, 4 chain. So 1, 2, 3, 4, and then the Br here. On the circle carbon, right, we have, looks like, did I forget? Yeah, I did forget something. There's like an H and a Cl. So I'll put like a Cl here. I'll put a, there's an H there that I won't have to draw in. And then there's 1, 2, 3, a 3 carbon chain. So look at that. And so I'll have that. Now, in terms of stereochemistry, right, you just want to keep everything relatively correct. For example, right, Br and Cl are anti to each other. So like if this were wedge, this would be dash. Right. And so then H and H are anti. So H and like that. Right. So this could potentially work. I mean, this is if I were looking at it from this perspective here, essentially. So that could work. Or could it? I guess the way that it's drawn, I guess if it were looking this way, the Br would have been on the other side. So it's, I guess if you can see it, you would really, what I've drawn is looking from here. So we should actually have it so that the Cl is wedged, if that makes sense. right? Because if you kind of imagine that your body is here, right, the Cl would be on this side as opposed to how I had it before. So we'd have a wedge here, which means that the Br will be a dash, right? And so this H will be a dash, and then there's an H here. It's a wedge, right? And so now you have a molecule that you can now name with the correct stereochemistry. You know, one thing I'll tell you is that in terms of the naming, I think it's always a couple of points, and I'm not sure how the extra credit works on it, but I imagine if you just want to get a name down, I'm pretty sure you can get at least some points for getting the name down, even if you don't get the stereochemistry down. So let's say that maybe you're not as confident as I am in seeing, you know, where things should go. I would at least try to get to this point here where you can actually have things down and just name it, and then you can worry about stereochemistry later. So I know that can be a little bit difficult. Okay, cool. But we'll call it there for now on that stuff. Again, I do want this video to be kind of short, not too long. Probably wrap it up in like an hour 15, something like that. Okay, cool. All right. Last question: which compound has the highest boiling point? I mean, this is just, you know, intermolecular interactions, right? Alkenes and alkynes don't really have like much differing in terms of boiling points. They're almost usually the same. This is that extra pi bond, right? So it's not too bad. Really what we're thinking about here is the fact that alcohols can hydrogen bond, right? So that's an extra intermolecular force that the rest of these do not have, that we have to burn through to excite to get them into the gas phase. So this would have the highest boiling point. So it's kind of a lab question, right? In your distillate, you guys might remember you guys have that distillate, right? Or distillation of your chlorine product from your alcohol. Alcohols have a higher boiling point, so you could boil out your chlorine while keeping the alcohol in there. That's why it was really important to understand what is the boiling point of your product, of your starting material, so you know what temperature you're allowed to get up to, like that will allow you to boil your chlorine, but not boil off your alcohol. Now, obviously, you do end up with some contaminants, right? At least in the case of the alkene, you might end up with a little bit of alkene, but yeah, whatever. Right. Cool. All right. So moving on then, nomenclature, use the online tool, you guys can figure it out. We'll move on to the predictive products. And as always, we do have 8 problems here, but we can easily expand this to 24 just by doing extra questions, right? And I'll always include them in the key just to make it easier for you guys, okay? But the first one we're starting with is R2BH on this diene. So you guys might remember R2BH, that's the reagent that we introduced with the alkynes. It is essentially the same as BH3. The issue is that BH3 has 3 of these hydrogens that can complex with a pi bond, and alkynes have 2 pi bonds. So you don't want to accidentally overreact. You know, if you use BH3, you might accidentally overreact with an extra pi bond with BH3, so that, you know, that could prove fatal or futile in your efforts to hydrate this pi bond. So we use R2BH just to get a single hydration. So we get that. So we get this here, or a single boronation, I should say, and then we oxidize to get to the alcohol, but it's an enol, so we get a tautomerization. So at least on the front of terminal alkynes, very reliable method to make aldehydes. Totally possible way to do it. Okay. So a lot of you might think that R2BH only works for alkynes. So that's not true. It also works for alkenes too. Because again, all you really need is a BH bond. In the case of BH3, you have 3 of them. So again, if I were to use BH3 here, actually the product would be both of these pi bonds could react, right? Because once you get to, I mean, you can imagine, like if I attacked on this one, it wouldn't really matter which one I started with, right? Once you attack on one of them, on the like the boron, I know it doesn't look really nasty, but boron will attack here. The other pi bond can attack, or actually probably from here, right, to less steric position, like that. So you'll end up with this 1, 2, 3, 4, 5 membered ring if you use BH3. So R2BH is just a selective reagent. It only reacts with 1 pi bond, and that's the point of this question. It's a chemoselective question. If BH had a choice, if it only had 1 hydrogen, it had to choice between who it wants to react with, who would it choose? Okay. Now, again, yesterday we talked about how 99% of electrophiles want to go to this highly sub-alkene. And that's usually just because, right, more nucleophilic the pi bond, the better it interacts with the electrophile. But remember, boron is incredibly sensitive to sterics, right? High sensitivity. And so despite the fact that, yes, this might be a bit more nucleophilic than this guy, right? Boron is huge, right, compared to carbon. So it experiences more sterics. So it wants to be in the most open position possible. That means that when boron complexes with the pi bond to react, it's going to choose this terminal alkene here. So in fact, R2BH will actually react with the terminal alkene to form the terminal alcohol. And I mean, if there were more boranes, then of course they would react here too, but we're looking at the other reaction here. Okay, so insane, right? Kind of an interesting little development there. Now, if I use like MCPBA or a carbene or whatnot, right? Obviously, then it would have gone here. So any triangle you could think of, I'll put A here, right? For any triangle you can think of, it would have went on here first. So you can think MCPBA with the oxygen. You could think, you know, dichlorocarbene, right? One equivalent would have went on that carbon there. Which again, remember, all of these are one equivalent unless I said otherwise, like here, right? And that's the case. Okay, cool. So that's the first one. And again, we'll just wrap it up there. We kind of talked about 2 extra examples. We talked about MCPBA would go there. And so would, I guess, I mean, if it was O3, it'd probably be excess, so it would cut here and here. But hey, let's actually talk about that down here, right? O3 excess, and then followed up by reductive zinc, right? We'll just essentially cleave on all those pi bonds as such, and we're just going to replace with oxygen. Okay, just like that. So I'm kind of cutting into the other box, but it's okay. You guys just make sure you don't do that like I did on your exam. Right, but we're just going to cut like that. Super, super simple. Nothing to worry about there, right? Again, we could have asked the same question of where would R2BH react? It would react right there, right? It would not react right here. Although actually it's a tetrasub, so definitely this pi bond is like, it's like an eternal hell for that R2BH, right? So it's definitely going to react there if we were to do a 1 equivalent of R2BH. Very common, actually a very common R2BH is the what do you call it? 9BBN, and 9BBN, usually the accepted terminology of 9BBN is a sort of like parachute. It's such a big group that we put on it. And in literature, you'll see like a parachute drawn on. It's pretty cool. Cool. All right. Moving on to C. Right, we have this alkene here, and we have hydration, non-rearranging hydration conditions. And so I imagine a lot of you probably did this instantly. Right, you drew out the products, and maybe some of you, when you're drawing this, were like, oh my God, Jim is an idiot. He didn't give us something selective for the methanol to attack on, so I have to draw both products for attacks here and attacks here. Okay, that, you know, he wrote the worst possible question. Well, I implore you to think even deeper about this, because yes, there is methanol in here as a solvent. That's really true, and maybe it could open the HG. But I think that something is faster. Maybe there's a faster alcohol. Maybe there's an alcohol on the molecule. Right, we could have an intramolecular attack that's way faster. Okay, and so we're going to have the opening on this side because it's closer and it forms a 6-membered ring. We open on the other side, it would form a 7-membered ring, which is not entirely favorable. Right, but we'll get this here. Technically, what the stereochemistry is of the other bond will depend on which side the HG forms on. So if it's like a syn ring, it would do this. It is possible for it to form an anti-ring. I know that might hurt some of your brains, which is okay. That just means that you guys won't just get you won't get a problem this complex, but it is totally possible for it to open up this way. Just keep in mind that HG just gets reduced into H, right? So that's why I didn't draw it in, but it'll get reduced to H with that NADH4 step. Okay, but again, you can imagine any triangle would have done this, right? So let's say that I did this with the BR2 triangle, right? That would have done this. It would have just formed the anti-bromine. The anti-bromine would have formed something like this. That totally would have worked. If it were, let's say, I mean, I guess the only other thing is epoxide, right? Epoxide would have done this too. Just would have opened that up. Okay, we just would have to add in an extra step of base or acid, right, to catalyze it. Yeah, totally. Alcohol would open that up. Now, an interesting question then is, what if I did this in acid? So I did this in formed a cation. There's kind of 2 answers here possibly, right? One is that we get the closure as usual. And again, it's a cation now, so we really don't know how it adds until we do the reaction. But another thing to consider is that, what if they could rearrange, right? What if this tertiary center could rearrange, and so we get this compound here, right? That's an interesting compound. That's a test-worthy compound, isn't it? Really, where in the world did this come from? How do we even predict this, right? Well, we call this a spiro compound, and it really would boil down to reaction kinetics, right? I mean, the alcohol is right there. Probably, I mean, it probably attacks faster than the rearrangement can happen, just because the cation has to form. before it can rearrange. And the alcohol is just right there. I mean, I guess you don't really know, right? It could be spinning because you have full rotation on this carbon. There is a potential for it to have time to rearrange. That'd be a cool one. Hard to predict though. I would imagine that predictions like this. I mean, if a cation rearranges, it'll be a very obvious one. Like it'll be one that you don't have to worry about competition of the alcohol swooping in or the H attacking. Yeah, cool. All right, so that we'll call it on that. And again, we did go over 2 examples. So that's pretty cool. All right, D2 PDC. So again, don't be afraid of D. D is just heavier than H, right? That's just H on a bulk. So it just means that you have to draw in the D. You can't just you can't just ignore it like you would with H. But when we look at the substrate, we have these kind of daggers on these substrates. So again, thinking mechanistically might help us here to understand this steric effect. But we have these H's on a palladium interface, and the alkene, right, has to essentially, like whatever it is, has to interact with that interface, right? So it has to come down, and that's how the hydrogenation happens, right? Is it kind of, the alkene kind of slams into it, and it's like, oh, let me take those H's, right? But imagine if I have something here, right, like a sharp edge, right, that's sort of preventing the alkene from, even getting there, right? Because it's bumping in before I can get there. It's like, oh man, like I have this. Oh, look at that. It's like a, what do you call this, pogo stick, right? That triangle or that steric is going to prevent hydrogenation on the space. So if we're ever going to get hydrogenation, right? Again, as with most things, we want to go opposite to the sterics, right? Because now, oh, look at that, easy, right? Whatever this stereochemistry is, doesn't matter. The hydrogenation will always be opposite to that face, okay? And so we can see here, we have 2 of these daggers just to really hone in the point that, hey, guess what? We are not going to get hydrogenation on the wedge face. We will get it on the dash face though, okay? And that's our one product. Now, this is prominent in a lot of reactions, right? Like this could have been a lot of things. This could have been dihydroxylation, right? So OSO4, right? That reagent is not going to want to interact with those 2 dimethyls, right? Or sorry, the 2 cyclopropyls. This could have been BR2, so BR2, so making the bromonium ring, and then opening with some reagent. So in this case, you guys would predict that opening with a reagent, like let's say CN minus or something, right? That's going to have to open on the same face as the methyls, but the bromonium initially formed on the down face, or on the dash face. Okay, so consider it, anytime you see something potentially sterically inhibiting, consider it a clue as to what you were supposed to think about. It's very likely you would have to think about it, right? One of my favorite questions to ask is this epoxide question, simply because when you think about epoxides, a lot of people just memorize, oh, if if both sides are equal, then we'll have attack on both sides. No way, man. No way is that going to happen here, right? If a nucleophile has to choose, in no universe does it tend to choose to attack on the same side of that terbutyl. Opening is almost exclusive on that right side there, okay? So always consider sterics, right? That's always a possibility. And it's something that the professor wants you to know. Okay? Now, a cool little thing, right? Let's say that I do epoxidation here. Again, obviously, epoxidation will give me the dash face, okay? But there is a way to get the wedge face epoxide, okay? And so to talk about this, I'm going to show you guys a substrate that I used to work on. This here is very similar. I'll draw most of it, but this here is a part of a body of a molecule I used to work on a lot, okay? And it has this pi bond here. But what's important is that we have this CH3 all the way over here, okay? This CH3 made things very, very interesting. I'm pretty sure I still remember what this looked like, so I'll try to draw it in a 3D fashion. But we would have this here. Okay, so this is the 3D structure of what I'm drawing. Okay, and then we'd have OCH3 like that. Okay, or this group here. We can just ignore this group for the most part. Okay, and then we'd have stuff here, but don't need to worry about that stuff. Stuff here, but we don't have to worry about that. Okay, cool. So when we're doing hydrogenations, or sorry, any reaction really, right? Again, this CH3 is going to play super goalie, right? If let's say, for example, we did a BR2, right? The BR2 reagent is always going to have easier time approaching from the bottom than it does from the top. So in this reaction, the BR ring always forms down this way. Okay. You can also consider that if I try to do MCPBA reaction, so MCPBA looks like this, right? Again, easier time approaching from the bottom than it does from the top, okay? So one of the difficulties we had when considering how to, I'll show you guys what we wanted to make, but one of the things was that when we wanted to epoxidate, it was forming on the bottom side, but we wanted on the top side. So what is some ways that we can overcome this, right? How can we get that top side epoxide to form? Well, we can form the bromonium, right? So it forms this here, and then we open it with water. So the reagents together would essentially be bromine and water, okay? And so what we would get, right, would be, so because we're, getting rid of the alkene, this is going to go back to a chair. But what we would get is a bromine and, yeah, we would get like a bromine and an oxygen. Now, if you guys had to guess where the oxygen went, you might assume, oh, the oxygen goes here, right? And then the bromine would go here. But it turns out that this CH3 plays such good goalie that actually the oxygen would add on this carbon here. Okay, so that's how crazy this is, right? I mean, obviously, you would never be expected to predict this. I'm just showing this to people that are willing to think a little more, right? Sterics on many occasions will override typical reactivity, right? Water had such a hard time accessing this carbon because of the the formidable CH3 goalie there, that it instead opened most of the time on this carbon here. Okay, and so what we would get is this structure here. This we call this a halohydrin, by the way. I know I haven't been going through a lot of vocab, but this is a halohydrin when we add OH and Br. Okay, and now if you were to add base, so OH minus or NaH or whatever you want, right? O minus could go ahead and clap down on that carbon to form an epoxide. So this would again kind of change the geometry of the ring, right? Because now it's going to be, right, it's a little bit different. It's not exactly this, but it's essentially, it's almost like a double bond is there with the ring strain. But now we would get the CH3 on the same side. Okay, so cool little reaction, right? Again, nothing that's expected of this class, but just wanted to, help you guys think a little more in this sort of thing. Okay, so that's how you can kind of reverse the selectivity. So if I wanted to, MCPBA, right, would give me the dash here. But if I wanted the wedge, all I'd have to do is start with Br2H2O, right, to form the dash bromine, and then close it with NaOH so that it forms the wedge epoxide. So cool little selectivity trick there. Okay, cool. All right. Now this Br2H2O reaction really sucked, actually. Everything on paper always works, right? But in real life, this gave a mixture. Sometimes you get dibromide, diol. Sometimes you get nothing would react. So really interesting substrates. Cool. Anyways, we'll move on now. All right, E. This is a very common sequence. You guys should all be very familiar with it. We're going to dibrominate, and then we're going to have excess base to form the alkyne. Okay, so this is essentially just turning your double bond into an alkyne. Super simple, right? So commit this to memory, right? Commit this to heart that this is the sequence you want to know. Okay, you can do any reaction too on this, just to practice, right? Like triangle or something, stuff like that. Cool. F, right? Again, alkynes, this H is particularly acidic, so NH2 minus can pull it off pretty well. To give some pKa values, NH2 minus around 35, alkynes around 25, which is kind of interesting because you would imagine N is more acidic than C via electronegativity, but it turns out that the sp orbital just overrides it. It's one of those exceptions that you just have to know. Okay, so we can go ahead and deprotonate that. Okay, and then when we consider where this is going to open up, whether it opens up on the more or less sub, right? Bases usually open up on the less sub. So what we'll get here is a 2-carbon chain, so 1, 2, with an alcohol in that second carbon, and that second carbon also has a methyl, so we'll go ahead and add that there. Okay. Now let's say that I attacked a carbonyl, because you're totally allowed to do that too, right? It would just have the alcohol a little bit closer, right? If I attacked like a carbonyl like this one. Okay. You can also attack alkyl chains too, so it usually has to be primary though. Won't work if they're secondary, to be honest. So we'll see something like that. Cool. All right. Moving on. Now, a lot of you probably saw this and saw, oh, alkyne anion. That's just essentially an SN2. or it can, it can attack things like we just saw. And I see an alcohol here. So maybe I'm thinking, oh, this nucleophilic reaction won't work, right? Because alcohol is terrible leaving group. So I write NR instantly. A lot of you probably thought to do that. That's okay. That happens. What you really want to watch out for here is that not only is the alkyne a strong nucleophile and that reaction doesn't work, it's also a strong base. And this is the part that takes precedent most of the time. So you should always ask this question first. What can a strong base do before you ask what it does as a nucleophile? Because the basicity part takes precedence. And so alkyne anion, right, when we consider if there's any acidic proton, there is, and it's the alcohol proton. Okay, so you can consider this as like a lithium exchange, lithium hydrogen exchange, where we deprotonate the alcohol to lithiate it. Or you just, think of it as an acid base. So great question is, what are the rankings of acid bases that I should know, at least for this class currently? And so I'll kind of rank them, right, from most acidic to least acidic, right? But these are generally the ones that you want to know. Okay, at least their order around each other. Cool. So sp3 CH versus sp2CH versus NH, SPCH, and then OH, like an alcohol, a thiol, and then the carboxylate, right? These are the general pKa rankings or acidity rankings. Values you can remember are the following for all of these. Trying to keep them like around a value that you can kind of, actually, if I just made this 10, then look at this, it's like 5, 10, 15, 25, 35, and then this is 40, and then this is like 50. Okay. This is more like 45 actually. Okay, so you can see everything kind of has like a 5 in it, right? So it's not a hard one to remember if you just commit some time to it. Okay. So essentially what this means is that, if you have something up here, it can deprotonate anything below it, but nothing can protonate above it, right? So if I start with RNH minus, I can deprotonate all of these guys, right? So I can go downwards, I can go down and deprotonate, but I can't go up. So N minus can't really deprotonate this sp2CH theoretically, right? Cool. So common tricks on this question, how I could have wrote this so that it was actually NR as something like this, right? Because this H here, even this H here, right? Neither of these are willing to be deprotonated by the alkyne. So this would be NR, right? If I had like, again, a triple bond, but maybe I had like an NH2, again, not willing to do that, right? Not willing to do that. So it's not going to happen. This is also NR. Cool. Things to think about. And finally, right, we have our alkyne here that we're just going to turn into the more sub-enol, which tautomerizes into the keto. Okay, pretty simple. So common question I keep getting is, how do I know when to tautomerize? Anytime you form an enol. It is not restricted to hydration, right? We saw that one reaction where if I do Br2 H2O, right, that'll form a bromonium with the OH more sub, Br less sub, that's an enol. So we get the alpha bromo ketone, right? So cool. Now, are there any enols that won't tautomerize? Yes, there's two examples you should be somewhat aware of, right? One is the phenol enol. It's literally in the name, right? But this guy will not tautomerize into the keto because, as you'll learn in the next section, this ring here, the benzene ring, is very stable, very sacred, and breaking it to make the keto is very bad. The other is if I took this alkynyl ketone and I hydrate it, right? Again, thinking about the effect, right? This is a withdrawing group, so the electrons are going to be pushed towards the carbonyl, right? The water will attack on that farther away carbon, right? When it forms this hydrate here, and I consider the tautomeric form, right? Again, higher instance higher instance of the enol than the keto. Why might that be? Because if I look at the p orbitals here, right, notice how the p orbitals are here all conjugated. Again, lowering energy system, right? Versus here, they're not conjugated, they're isolated. So another example of when you might want to be aware of that. But outside of this, outside of these two, really everything else tautomerizes. Okay, cool. All right. So predict the products. Again, you can do really any two on this one, right? Just gotta do something with alkynes. Cool. So now we'll go into mechanism. I didn't really have time in the last video to talk about mechanism. So I do want to spend some time doing that today just to talk mechanism a little bit. I know that, again, it's one of the it's the toughest thing when you go from A to B, right? A, you had like 5 mechanisms to know, and now you know like 100 of them, or at least it feels like 100, right? But, if we look at the document that I made, right, again, the big part of this document to help you guys is to kind of organize the reactions, right? To kind of help you segment, how to think about them, and if you had to make an educated guess, what it could be, right? So we have the acid mechanisms, which again, for the most part, form a cation. If there's anything a cation might want to do, like rotate, rearrange, right, move around, it's going to do it. So that's what to think about there. So most acid mechanisms can be categorized as such, and the hardest ones are the rearranging ones. Triangles are by far the best mechanism because they're all the same. This is the reason why I drew this, and I drew A and LG. This is all the same. All mechanisms involve some electrophilic atom, so A, that is attacked and it attacks back to form a triangle, and you lose some leaving group, right? That is basically every single mechanism for a triangle, right? I mean, you can just like cold call, right? Let's look at the acetate, the MCPBA, which is actually the one on this one here, right? Actually, it's right here, right? As long as you know what MCPBA looks like, you can always get this right? Because all it is, again, is MCPBA makes an epoxide, so you're going to attack this oxygen here. So we'll attack it, the oxygen will attack back, and we will lose leaving group. Now, the arrows here are a little different. You'll actually move this arrow here to this bond, and then this carbonyl will attack the H. But that's just so that when you form the products, you resolve with a carboxylic acid side product, which you do have to draw in, by the way. Again, for this one in particular, it's a ring here with a Cl 1 carbon away. That's the MCPBA reagent. Okay. But again, that's it. That's all it is, right? Let's say that I have a bromine, right? I didn't trick you guys. You attack back, and you lose bromine. And guess what? In this case, you don't have to do anything crazy other than if there's a nucleophile, it will just attack somewhere, right, to open it up. And then, right, there's specific stereochemistry, like let's say this was a wedge, right? Then the nucleophile must be dash, it must be anti. Okay. So triangles are a blessing in disguise because every triangle is the same. Even the carbene, which I know some of you guys struggle on a little bit, carbene is pretty much the same too, right? All it is, it takes a little bit of preparation. So in the N2, right, we lose the N2, which is the best leaving group in the world. And what we end up with is a plus minus species, which is equivalent to that, the double dot, right? That sometimes people have a hard time thinking about. I think it's easier to think about carbenes like this because it really shows you what I mean by the attacking and get attacked, right? There's an empty p orbital for this pi bond to attack, and then there's a full p orbital for the pi bond to be attacked from. And so that can really help guide your arrows in showing you, oh, that's how you make the triangle, right? Dichlorocarbene only really changes in that you have to set up both charges, right? In this case, the diazomethane, the anine's already set up, but we have to set it up in the chloroform, right? We take off the proton, and then this chlorine here just kind of falls off to set up the cation, and so there you go, right? If I have a pi bond, right? Again, minus attacks, alkene attacks cation, and what we get out of this is going to be a dichlorocyclopropane. Okay, so look at that. Nothing's too crazy. Triangles are quite literally all the same. So let's all come together and pray that there is a triangle mechanism, because 90% of you guys can just get that right on accident just by remembering this. Okay. The only time this gets a little hard, I suppose, is when you have intramolecularity, right? Because then you have to keep in mind that the nucleophile that's opening it will be this guy here. So again, let's do the mercuric acetate mechanism. Attack back, lose this guy off, right? One of the acetates falls off. And what we form is the Hg dude here. But again, all it is that this guy will just go ahead and attack. So we attack on the more sub side. That also forms a 5-membered ring. Again, my counting method that helps me out is 1 attacks 2, then everything in between 3, 4, and 5. That tells me that I make a 5-membered ring with the oxygen in it. And if I kind of number it, so 1 attacked 2 like this, right? Again, 2 has this kind of carbon sticking out of it, so I can draw it in. That's going to have the Hg initially. So I'll keep that as a placeholder. If there's anything on 3, 4, and 5, just add it in. So if 5 had a dimethyl, put the dimethyl on 5. Oh, thank you. Thank you. Sorry about that. 3 has an ethyl, draw 3 on an ethyl on 3. Okay. Do what you got to do, right, to get it right. But now we have this here, which again will initially be protonated. A lot of people ask me about this. You can deprotonate this, the acetate. Anything in solution can do it, honestly. You can deprotonate that. And then I hate this so much, but apparently you guys do need to know this for some reason. But apparently the H does an SN2 here. It doesn't actually. It proceeds to be a radical, but we're just going to go with this because it's in your lecture notes, right? So I'm kind of drawing a lot of things here, but again, thinking about how we can just very easily, get all this right. Triangles are a blessing. I absolutely love triangles. Okay, so none of these triangles should really throw you off for the most part. Most of them are fairly simple. Just pray for a triangle. Where things get a little more difficult are the crown and the Trojan. And I do really want to talk about the boration reaction because I know that's the one that's been troubling a lot of you. So let's actually even start with that. Let's talk about the hydroboration reaction and a way to remember that one. Because yeah, we can remember it's a Trojan, but Trojan horse doesn't help us much more out of that. What else can we do? So we'll consider the BH3 reaction with BH3, although I believe that the reaction is best asked when it's R2BH, and you'll see why. Because a lot of the mechanism, I know it's 16 steps, but it's really only 16 steps because so many steps are repeated because it's BH3. Okay, so we'll start with the simple substrate. But the first step in this reaction is setting the anti-Markovnikov. So set anti-Markovnikov. That's the first step of this reaction. Okay, so what do I mean by that? Remember, in the BH3 reaction, the first step is we complex the B and the H, complex with the pi bond, so that we get the borane onto the alkane essentially. So the pi bond attacks borane, H attacks back, and what we get is this here. Okay. Now you don't necessarily have to draw in the H, but you do need the borane drawn out. But we still have 2 of these bonds here, and again, just kind of do the same thing. So just make sure that you have the borane on the side, the left subside, right? We'll have that there. So we're just doing the same thing 3 times. We're setting up the anti-Markovnikov. If there's 3 H's, then we just do it 3 times. R2BH is a lifesaver here because if it's R2BH, you just kind of do it once, right? And so you can skip out on doing all these extra steps. So rather than memorize that you have to do all these things, understand what you're doing, right? You set the anti-Markovnikov, and then we'll do the last one here, right? Where this attacks here, this attacks here. And what we get is this. So the trialkyl borane. So now we are set up. So we've set up the anti-Markovnikov. The next step is replace B with O. Remember, the whole point of the boron is just to get the anti-Markovnikov selectivity. Once the borane is on, we've got to replace it with oxygen. So how do we do that? That's the second step, right? The NaOH with the peroxide, right, starts to form, right? So for not really reasons you don't know, but this OH minus here can relatively easily deprotonate a peroxide. Peroxides are more acidic than hydroxides because the OH actually acts as a stabilizer for this lone pair here. But anyways, whatever. On the side, we'll be forming this peroxide solution. And that peroxide solution, right, essentially serves, wait, 1, 2, 3, yeah, sorry, right? That peroxide solution essentially serves as your oxygen donor. Remember, boron is an electrophile, so O minuses definitely have no problem attacking into here. And so what we get is this species here with the boronate. And again, all we have to do now is set up or replace the boron with oxygen. So how do we do this? We do that weird push-pull where an alkyl chain attacks the oxygen and we lose off OH minus. And in doing so, we have now begun the replacement process, right? And oxygen has now successfully replaced a boron, right? Because now look at this. Instead of having the boron at that anti-Markovnikov position, we now have the oxygen. Okay? So we're just going to repeat this 3 times. And again, because we're all in this together, I'm going to go ahead and do it all 3 times just to show you. It's just it's a bunch of repeating the same steps over and over again. That's why it shouldn't scare you guys. But again, we're going to have this here. And once again, alkyl chain attacks the peroxide O to set up that oxygen in that anti-Markovnikov position. And we're going to do this one more time. One more time for the gram, right? We're going to add in boron. I guess I'll put it over here, just so it's right next to the alkyl chain. And then again, we're going to attack that O, release out hydroxide, so that we get out this species here. So we now have our kind of like a boronate ester, I guess. I guess that's what I would call it. But now we have our, oxy chains or whatever. We have our alcohols ready to go. So again, set up the anti-Markovnikov with boring. That's what we're doing 3 times. And then once the boring is there, we've done the hard part. We got the boring on the anti-Markovnikov. Now we send in, we presented the alkene with the boron horse, and now the soldiers have come to attack in whatever, I don't know. Anyways, we've now, in the second step, replaced the boron position with the oxygen, right? That's the point of that second step. And again, we're just repeating the same thing over and over. That's why it feels so long, but it's really not that bad, right? The last step then is just hydrolysis, right? Release the boron, because we don't need the boron, right? It's just holding on to all these chains. We've got to release these guys, right? So how do we do it? Super simple. We're just going to attack with, I guess a peroxide could do it. Anything could really do it here. It doesn't really matter. I guess I'll just use hydroxide because that'll make things simpler. But right, we can have the hydroxide in, and out plops out one of those alcohols. And look at that. Well, actually, it's not an alcohol, it's an alkoxide initially. But this will usually just deprotonate that to become the alcohol anyways. Okay, but look at that. Now we've set up our first alcohol. Right, so I'll just kind of do that deprotonation in my brain. Right, and now we have our first alcohol. Right, hey, guess what? We're just going to do this all over again. So OH minus is going to go ahead and attack in. I guess it's kind of weird to see this, so I'll just protonate this. We'll get this. Guess what? We're going to release out another one. Oh my God, so beautiful, isn't it? Hopefully it's all starting to make sense. I'm going to kind of just speed run this part because, again, it's all the same. But look back at your notes of what particular arrows were done here specifically, just so, because I'm just doing what I would have done, or what I kind of think or what I kind of learned. But anyways, yeah, we're just releasing out these alkoxides by attacking the electrophilic borane, which is, it's always been its job is to be an electrophile, and then kicking off those alkoxides. And what we end up with is a boronic acid, which again, I didn't, it could have been deprotonated, doesn't really matter. This will just make Na3BO3, right? So a boronate. But that's all there is to this mechanism, right? Again, it feels so intimidating, doesn't it? Because it's like, I count all the steps, it's 16. In reality, it's only like 6 steps, right? Really, if you do the R2BH, look at how much simpler this is if we just do R2BH, and it helps to make sense exactly why we're doing what we're doing, right? Oops, sorry, I set this up wrong. There we go. Right? If I do R2BH, right, I get 1 complexation, right? I then get 1 attack by the peroxide. So I set up the anti-Markovnikov. I then replace the boron with the oxygen. And then I do my hydrolysis. Wow. Oh my God. You're telling me that this is actually only, hold up, I can't count. Let me just finish this real quick. and then I'll count it. But this will just leave. Voila, 1, 2, 3, 4, 5, technically 6. You're telling me this is a 6-step mechanism actually, and there's 10 fluff steps? Yeah, that's literally what I'm telling you. Okay, so don't overthink it. You're just doing a bunch of, repeat work. I think this is a perfect question to ask in this form where it's R2BH. Because then you don't got to stress about it, right? You're only doing everything once. You're showing you understand. I mean, you guys saw in your notes. You guys saw that the professor literally annotated all the extra additions because there are so much repeating steps. So I will pray for you guys that when you get this question on your exam, it's presented as this. It's presented as how does BR2 or R2BH react with an alkene or even an alkyne, right? If it's with an alkyne, it's even, I mean, the only issue is that you'll have to do the tautomerization steps. You'll get to here, which I highly recommend you guys do that. It's the same thing we just did with R2BH, and then you just have to do the tautomerization, right? Which tautomerization can be a little, that can always be a little nerve-wracking, right? But again, you're in base in this solution, so you get O minus, and then this will go out and re-grab that proton it gave to the base, and you'll have out your aldehyde. So that's all you add if this is an alkyne. Oh my God, so beautiful, right? So hey, you know what? Since we're talking about tautomerization, let's just quickly do the, let's just very quickly do the acid one, because again, it's so quick, right? Let's say that in acid form this guy here. Super simple. Now you're in base. Sorry, now you're in acid, so you can attack a proton. Okay. And then the solution just takes back the proton you stole from it, right? Any base can do it, like usually water, because usually you took this from water. And voila. Out you get is the beautiful ketone. Okay. So hopefully you guys are starting to see how simple this is. It's very common to overthink these. Very, very common. I think really the hardest ones would probably be the crowns. I don't think you guys know this one, the osmium one, because the osmium one, I remember it doesn't really have. Oh, I didn't even make these send. I messed that up. My bad. The osmium one doesn't really have. I don't think you guys talked about the hydrolysis of the osmium ester, but you should know the crown, which I'll go over again today, and then we'll call it there on the mechanisms, right? Just to save some time. But with the crown, with the ozonolysis, right? Again, it can be kind of terrifying, but it's not too bad. Okay. Again, it's two. It kind of has a pattern to it. Okay. So the minus attacks, and then this attacks back, and this goes on the oxygen. And what we form is the malazanide, I think, or the ozonide. You never remember. It doesn't matter where you put it. I know this is trans and I made it cis now. Actually, maybe the easier thing might be to do this just so people don't get mixed up, right? We have this, and then we get what we call a retro 1,3 dipolar. So we got it so we initially got a 1,3 dipolar. So this is a 1,3 dipolar reaction. And then we do a retro 1,3 dipolar. So this kind of just falls apart. Okay. Oh, I guess we can do, so this can go here, this can go here, this can go here. Oops, sorry, like that. Okay. And so if we kind of follow the arrows here, we're breaking this bond here in between the two carbons. We're forming a carbonyl up here. Okay. And then this species here forms this here. Okay. So we get out this really weird looking reagent, but if we kind of look very closely, if we look very, very closely at this, all we've really done is remake the 1,3 dipolar reagent. That's all we did. We remade the 1,3 dipolar reagent. Okay, so we're going to do another 1,3 dipolar, but this time the carbonyl. So this guy here has to be flipped over so that the minus is going to attack the carbon. That's how it works. And it's going to attack here. Okay. So we get a 1,3 dipolar. We get a decomposition, another 1,3 dipolar. And this 1,3 dipolar product is a bit more stable. Okay. Because it doesn't have 3 oxygens in a row attached to each other. Okay. But we get this here. This is the malazanide. No, ozonide. I believe this is the ozonide. Okay, this is the malazonide. Should be correct. Okay. And so this was in the first video where I was stumbling, but it's okay. In this step here, whatever your reductant is, whether it's sulfur or zinc, doesn't matter. We'll just use sulfur here. But the idea is you always want to break the OO bond. You want it to attack the sulfur, and then the sulfur will attack either this oxygen or the other one, right? It's up to you. You can imagine this bond is the weakest anyways. But let's say we choose to attack this, then we can push this bond next to the oxygen over here, and then push this bond over here, okay? And as a result, that will give us a carbonyl with that top oxygen there, and a carbonyl with this bottom oxygen here. And we have our ozonolysis product. So look at that. 1,3 dipolar, decomposition, 1,3 dipolar, decomposition. That's how we can remember this one and make it a bit easier. Now, the arrows are always a bit tricky with these reactions. They can always make things seem very, scary and, a little, it almost feels unfair. But, I just realized that these arrows, I guess if I want these to make sense, I'd have to look like this. Oops, sorry. So this would go here, and then this would go here. Yeah. Did I mess up? Oh man, you would think having done this twice, I would know how to do this now. I guess not. This definitely goes here. This will go here, and this will go here. There we go. Okay. So how can I resolve this? So I just break the middle bond here. That OO bond I'll push onto. I guess if I want to make it at this point, actually, honestly, it doesn't matter. But if I want to make what I have currently, then I should do this. I should break this here, push this here, and then, what am I messing up? I just had it. Hold up. Let's go back to when I had it. Okay, that works. So, or does it? No, I don't think so. Why am I blinking? Sorry, it's a little late. I think that's why I'm blinking. Maybe if I start with that, well, no, that doesn't help at all. I do that. Am I going crazy right now? I imagine probably already know, and you're probably screaming at your screen. I don't know why I always mess this one up. What am I doing wrong? This breaks this way. Oh, wait, no, that still doesn't work, does it? Should I draw something wrong? I don't think so. Okay, well, I'll admit it. I am I don't know what I'm doing wrong. Or maybe I am drawing it correctly. I just can't see it. I don't know. Whatever. This one also, I mean, this one gives me nightmares, clearly. But whatever the case, it's all good. I'm probably just overthinking it somewhere. Or I'm probably using the wrong electrons on something. But anyways, whatever. I'll try one more time, I guess. Maybe. Oh, duh. That's what, yeah, I was using the wrong electrons. I forgot you would use this here. Okay, cool. Anyways, whatever. Yeah, I'm clearly not the genius that I make myself out to be, right? Anyways, O3. If I can't do it, you guys can probably do it. Cool. All right. Well, we'll call it there on the mechanisms. Clearly, my brain is fried. But let's go back to, this document here. But yeah, anyways, use this to guide you in your thinking and helping you organize the reactions. When it comes to alkyne reactions, they're really the only mechanisms you would want to know. I mean, they're all pretty much the same. To be honest, no one really knows how alkyne mechanisms work because no one wants to pay to study them. So we assume they work like alkenes, but they really don't. The only one you'd really need to know is R2BH or like mercurium or something like that. Outside of that, don't stress too much. Cool. All right. So mechanisms, pretty simple. Okay. Cool. All right, let's get into synthesis and then finish off with the NMR. These syntheses were a bit more difficult. We'll come back to this one. I think this one is easier than the top one. But hopefully you guys try these out. Again, when I think of these syntheses, I'm trying to look for patterns, things to help me out. For example, when I'm looking at this here, it might be hard for me to kind of rationalize where these 3 carbons are. But what I can do is take this alkyne, right? I can take this alkyne here, and the functionality, right? The alkyne functionality, functionality breeds functionality, right? So when I think of where these alkyne carbons can be, I'm really gravitating towards these 2 carbons here, right? That's my initial thought, in that, oh, you know what? That alkyne, right, is a pi bond, and I can totally see it forming an alkyne in the future, or sorry, an alcohol in the future. So I'm inclined to believe that, okay, these 3 carbons here, I might assign these 3 here. So carbon 2 is essentially where the alcohol is forming. And so if I'm saying that, that means that I'm adding in these 2 carbons here. So I'm doing some kind of Grignard reaction, right? Now, Grignard, or at the very least forming a CC bond, well, we learned this is very easy with alkynes. If anything, this is kind of a great setup, right? We can choose to add in either the ethyl or the methyl very easily just by doing, like an SN2 type reaction, right? We can do NH2 and add in one of these 2 groups. Now, I know which group you should add in, so I'll actually do something here. I'm going to choose the correct group to add in of the 2. I'm going to go ahead and add in the CH3, and hopefully it makes, we'll talk about why at the end it makes more sense to do this one than to choose this one here. But we can start by setting up that first methyl, even if we can't set up that second ethyl immediately. We can do it with this SN2 reaction here. Okay, so we'll get on that methyl, and so now we can kind of see that, okay, these 4 carbons here then kind of make up our entire chain. Right, so 2, 4, right, 2, 4. That's our entire chain. Now, when I look at what I have left, I have an alcohol, right? So a functionality looks like it's coming here, and then I have a carbon chain that I'm forming, right? And the carbon chain is particularly vicinal to my alcohol, right? I mentioned this. Anytime you have an alcohol and something vicinal, something new that could be a nucleophile, potentially, this is a very good signaling element for a functionality we want to use here, right? What's the functionality where when we open it, we get an alcohol and the nucleophile vicinal to each other, right? Starts with an E, ends with epoxy, right? It's going to be an epoxide. So this was supposed to be a signaling element for potentially an epoxide opening, right? And again, actually, it doesn't really matter whether these are like this or like that, because there's no absolute stereochemistry, but I'll just draw it the way it's drawn, okay? But this is an epoxide that was opened up with this Grignard here, okay? Now, in order to form an epoxide, we can't do that from an alkyne, otherwise we would have learned that. But we can make it from an alkene. That's just MCPBA, or the BR2 route if you want to take that, so BR2 into NaH. But how do I go from this alkyne to this alkene? Right? Particularly the transalkene, right? Because that's what I chose. I want to use that Birch reduction, right? NaNH3. Now, again, because there's no absolute stereochemistry, you could have gone the other route too. You could have gone Lindlar's catalyst into MCPBA, and then opened it up, because again, no stereochemistry, right? So who cares? But a viable route. Okay. So again, what were kind of the telltale signs? What were the signaling elements for this synthesis? What really gave it away? Well, the biggest thing is that we've added a Grignard, where we added 2 different Grignards, or 2 different new carbon chains, right? That's got to be, from an alkyne, you can just add one of those in. I chose a CH3X, and we'll go over why in a second why that was a better one. But when we just try to figure out where the second one came from, right, it boiled down to the matter of, right, OH and carbon chain vicinal to each other, right? What else can I do with that, right? What does that tell me, right? And that's why knowing your cues, knowing the synthetic tells can really help you out here. Because maybe you only have like 50 minutes on the exam, right? You don't want to spend 40 of it trying to figure out what this is, or trying to brute force this, right? A lot of you guys I've noticed have been brute forcing these syntheses, which is totally fine, but just retro it. Look, we do in 2 seconds if you retro it. Okay. Now there's a bit of a cheat code in this one because I didn't really think very hard. But technically you could have hydrogenated this, osmolysis this, and then done a Grignard here. Someone figured out something very similar to this, but not quite exactly this. But you could have done this, and I would have accepted it. It's one step more efficient than the one that I came up with. I would just kind of, if you think about it from the retro perspective, where you're trying to look at where these carbons are to this one, right? You can see where mine come from. But I mean, both indices work. Yes, this one's better, but I like this other one because it helps you think. It forces you to think more, right? To understand, to consider where these things are coming from. Okay, cool. All right, so that is going to be the second synthesis. I think is easier. First one's a bit harder because when you look at it, it kind of feels like a typo, right? We are going from, well, we can ignore the 6 member, but we're going from like a 3-carbon chain to a 4-carbon chain. So once again, when we look at this, instantly thinking comes kind of Grignard. But when we look at the location of that Grignard, oh my God, that's like that's not even near any functionality, right? I mean, if it were next to like an alcohol, I could think maybe like a Grignard. Maybe I could have thought like an epoxide because this is, maybe, but the BR2s here, like when I think about retrosynthetically where those come from, right? That's just the reaction with an alkene, right? And so, I mean, alkenes, they can come from alcohols or they can come from bromides. So maybe just for the time being, I'll just put like, there could have been an A here or possibly an A here. I mean, this is a bit of a difficult question because the question becomes, how in the world do we add this random carbon? So this problem I wrote specifically because there's something that always goes around during this time. Like you're taught a certain rule and everyone kind of says, oh, if you know this, you'll always get it right. And it's always bugged me because it's not the most correct rule you could use. But I guess I'll go ahead and spoil it here. But, when you guys are taught about ozonolysis, there's always this talk about ozonolysis is breaking CC bonds. So when you lose carbons, you know to use ozonolysis. And I agree. For the most part, yes, that can help you with the simpler questions, right? For example, right, if let's say I wrote this question as, this going to, or sorry, sure. Like this going to like this, right? You lost carbons there. So it's super easy to see how ozonolysis is applicable, right? Probably just, turn this into an alkene and then ozonolysis that, right? You'll get the aldehyde and then you can do a Grignard to get to there, right? So it's super easy to see the ozonolysis there. But I think the better way of thinking of ozonolysis is it's more of like a carbon chain reset, right? Because when you do an ozonolysis, yes, you are losing a carbon chain, but you're also given a second chance, right? Because, let's say you have this here and you're like, I want to ozonolysis that, right? Not only are you cutting off carbons, but you're given a carbonyl, an aldehyde, which you can then add more carbons to, right? So you don't have to essentially lose carbons and call it a day. You can also just reset the chain. So if I consider that this alkene here is the formation, I guess it'd have to come from, oh, okay, this one actually, I can see how this one now kind of sucks because this would have to come from, like if I want to think about ozonolysis, it have to come from a carbonyl, or sorry, yeah, carbonyl. This reaction is PBr3, by the way, and this would just be like a bulky base elimination. But if I consider this alcohol here, right, is from an aldehyde. Okay, look at that. I can add any Grignard I want to, right? I don't necessarily have to have it that it's a shorter chain. I can reset the chain. I can make it whatever I want it to be. Okay, so very complex problem this one is, but I wanted to open your guys' eyes to the total utility of the O3 reaction, right? It isn't just, oh, you lose carbons, right? It's you lose carbons and then you're given a carbonyl that you can add a new number of carbons to, right? So I chose to decide, hey, you know what? Let's get rid of that 3-carbon chain, reset it with a 4-carbon chain. Or I guess really it's you losing a 2-carbon chain, you reset it with a 3-carbon chain, right? So that's what I did here. So I added in this organometallic, right? Got in this, PBr3 to the bromide. Oh, this is actually going to be super long now that I think about it. So my bad, because then this would, I guess in my head, I thought it was like not that long. So my bad. I imagine some of you are trying to follow my rule, which I said like try to make it within 5 steps. This is like 7. I apologize. This you'd have to go through the bromide again. Oh my God, my bad. I should have just started it from here. ended it here. 1, 2, 3, 4, 5. Yeah, my bad. But I guess this is an easier. Yeah, this is definitely an easier way of seeing it if you start it from here anyway. So I apologize. I wrote a bad problem. Happens. But starting from here, it's way more obvious to see what you need to do, right, to reset the chain and get out a better answer here. Okay, cool. So again, hopefully that opens you guys' eyes up to that. In terms of other syntheses, can't think of any others that might be useful off the top of my head. No, not really, I guess. Actually, I guess I remember seeing one. It was one that was kind of interesting. I think it was something like this. Right, going from here to it's something like this, yeah. Right, going from there to there. This isn't too crazy. It's just chemoselectivity, right? If you do Oz analysis first, you'll break this bond for sure because it's more electron rich and this bond. So to prevent that, you epoxidate first. I remember seeing something like this somewhere. And then you can do your Oz analysis. Yeah, but that's not that cool, not that fun. But yeah, so hopefully these kind of open your eyes, help you see more. Let me actually look at the third one. I definitely don't have time to go over the third one in this video too. I apologize, by the way. Let me just open that up in this PDF viewer. Yeah, you can kind of see, I mean, this is a great example of an Oz analysis here, just because it's breaking a CC bond and you can clearly see it. So definitely a much more fair example of that. Tetrahalides really showing off what they're supposed to be doing there. But yeah, cool. All right. So let's go ahead and let's finish this off. I think the video is nearing like an hour and a half anyway, so I want to finish this soon. C7H8O. I mean, honestly, I'm just instantly looking down here to see what I can see. I see activity around 60-80. That probably tells me alkyne, to be honest. Yeah, that's probably telling me alkyne. So I'm thinking alkyne. I see that there's two lines here, 100 to 150. Two carbons required for an alkene. So I'm thinking alkene in here. So alkene, alkyne, that's 3 degrees right there. I think what's the total amount of degrees? So 7 times 2 is 14 plus 2 equals 16. 16 minus 8 equals 8 over 2, which is going to be 4. So we need 4 degrees here. So we have 3 currently. I don't see any other degree in here because we figured out this is an alkene. These two are going to be alkyne. You might be thinking, oh, is this another alkyne? Can't be, right? That wouldn't work because we need another line here. And that would be 2 more degrees that we don't have. We only have 1 more degree. So this is probably a hidden degree in this. Yeah, probably a hidden degree. I'm thinking the hidden degree is a ring. And when I look at this, 7 carbons, I like to just like subtract 2 to think of a ring. Well, actually, first off, I guess what we can think of is what is this oxygen doing in here, right? Is it functioning as an alcohol? Is it functioning as an ether? I don't see any alcohol peaks in this at all. So I'm thinking it's an ether. So now I want to think that this is some kind of cyclic ether. So it could be like a 6-membered cyclic ether. So 5 carbons in, and that would mean 2 carbons outside. So 2 carbons outside somehow. Do I like that? Well, there's going to be an alkene and an alkyne. So this actually won't work because that would mean that I would need an alkyne like this, and then maybe like an alkene here. Does that fit? Let's see if that works out, right? No, because there's CH2s that I can't resolve. So that makes this problem harder. So since there's no CH2s in this that I can resolve with this structure, I'm going to go with the 5. But I mean, if I were you guys, I would probably just write down stuff like DOU, which is 4, DOU, and then I would write ring. I would write alkene. If I look in the alkene region on this, so like 5 to 6, I see 2 protons active, so I know it's a disubalkene, so I could instantly write this. I know there is an alkyne. Now, whether it's terminal or internal, I guess you'd have to guess here because there's no IR information, but alkyne H's tend to show up as singlets around 3, and we do see as a 1H around 3, and we do see a 1H there. So I'm willing to bet that that's that dude right there. So I'm willing to go out on a limb and say that. And so, I mean, that's the fragments I'm writing in. I think it's a cyclic ether that's 5-membered. So now I just got to kind of put things together. Now, obviously, the alkyne can't be in the ring, but the alkene can be. So the question is the alkene going to be here, or is it going to be here? And so the main guiding force in this is looking at the alkene protons. For normal alkenes, where they have no structural influence, like no EDG, EWG influence, these guys tend to have like 5 to 6, right? The protons tend to mush together, really close together, because they're not very different. They're chemically the same, right? It's EDG and EWG effects that kind of cause these huge canyons, okay? So if I have 5 to 6 to 7, right? If I have an EWG, something that's taking electrons, like for example, a ketone or a carbonyl, for example, if a carbonyl is taking electrons from a pi bond, you usually see a peak that's really high up and a peak that's really high, like really low, but they're both usually within 6 and 7. So it's like a whole ppm difference, 6 and 7, right? That's what we usually see. If it's an EDG, like an oxygen, right? It's usually the same separation, about 1 ppm, but 5 and 6. So it's lower on that spectrum. Okay. What I see here is a 5-6 separation by 1 ppm, and it's very, very different. So I'm willing to go out on a limb to say that this pi bond is right next to this oxygen. And so if I think about the H's here, right? This oxygen donates electrons into this carbon particularly. So this H is going to be the one that's at 5. This is the one that's over at 6, okay? And the one at 6 is a doublet, so it only has this neighbor here. And then the 5 is a doublet of doublets, which is just a very fancy way of saying a triplet. So we'll have something like this here, okay? Now I know for a fact that there's got to be something here like this because there's no 2 H's, so they can't be a 2H. So now I just kind of have to resolve these two things here. One of these is going to be an alkyne. The other one's going to be, looks like a CH3, I guess, right? So, well, yeah, so we're going to have an alkyne here. Yeah, okay, yeah. So one of these is a terminal alkyne. The other is the CH3. So I guess you kind of just draw these in. So it's either this or it's that. So the question becomes, which one is which? I suppose it depends. So this oxygen is neighboring this guy here. Let's see how many neighbors this guy has. So this proton is probably going to be around like 4-ish, above 4-ish. Maybe I think it's this one here. So it's a pentet. Pentet means that it's got a lot of neighbors, which would not be the case if it was next to the alkyne. That would be this H here. That's a pentet, right? Because that's 3 there and it has 1 there. So definitely going to be this structure here. Okay, cool. So, I mean, I guess there was a little bit of hindsight bias. I didn't totally remember what this was, to be honest, but I guess I was a bit more confident because I could kind of see where this was going. You could try to emulate how I do this. Really, it's a matter of just looking for patterns and putting things together. I treat NMR as you try to get as much partial as possible because it's usually like 10 points, but you get like 5 in partial. The other 5 you just leave up to God or whoever you pray to, right? But cool. All right, that's practice midterm 2. Hopefully you found that helpful. I'll try to get this out with a key shortly. Yeah, cool. If it's any issues, please let me know. You guys have a good night.